The theoretical description of the atom has advanced over the past century, from Thomson's plum-pudding model to Rutherford's and Bohr's planetary models. To today's atomic orbital model. The atomic orbital model is a currently accepted model of the way electrons are arranged in the atom. Let us outline how the Bohr's model was adapted and further developed into the atomic orbital model. Bohr's model has electrons orbiting the nucleus in a circular orbit. There are orbits at different energy levels. Each of these energy levels, or shells, can hold a certain amount of electrons. Also, each shell is labeled using the lowercase n. So in the diagram, the shell where n equals 1 is the lowest. In the atomic model we use today, we still use this energy level concept. Today, n is called the principal quantum number. In today's atom, each energy level or shell may consist of sublevels or subshells. Electrons are no longer thought of as discrete particles. Today, electrons are described as possessing wave-like properties. Because of these wave-like properties, their orbits around the nucleus are not just simple circular orbits as in the Bohr's model. Instead, their orbits seem to follow irregularly shaped paths. Some are shown here. These shapes are three-dimensional. For instance, this is the shape of a three-dimensional sphere. Instead of referring to these shapes as orbits, we call them atomic orbitals. You can think of an atomic orbital as a calculated region in space where there is a high probability of finding the electron. If we had to draw an analogy, let's say that a planet represents the nucleus of an atom. Then, in the Bohr's model, a spacecraft orbiting that planet would represent an electron orbiting the nucleus.
Phone home.
For today's model, if we use a tiny planet to represent the nucleus, then an atomic orbital would be represented by the planet's atmosphere. So today's model would be analogous to a tiny planet with a huge atmosphere. And this atmosphere may take on different shapes. Now, at any location in the planet's atmosphere, there is a good chance that you will find a molecule of air. Similarly, in an atomic orbital, there is a good chance that you would find an electron. So an atomic orbital is not just a pathway that the electron would follow, but rather a region in which there is a high probability of finding an electron. The atomic orbitals are named as follows, where X is the energy level or shell corresponding to the principal quantum number n. So we can have an n equal 1 shell, n equal 2 shell, and so on. Type is a lower case letter denoting the shape of the orbital, and Y is the number of electrons in that orbital. Let us see how we have broken down the arrangements of electrons so far. We have the nucleus at the center, and the electrons can be found at different energy levels or shells, which are represented by the principal quantum number n. Within each of these shells are subshells, or atomic orbitals. Each subshell has a unique quantum number L, which is called the azimuthal quantum number. L describes the orbital angular momentum of each electron. Now L is dependent on the value of n, such that L can range from 0 up to n minus 1. L can only be an integer. So for the n equals 1 shell, L can only be 0. For the n equals 2 shell, L can take the values of 0 and 1. For the n equals 3 shell, L can take the values 0, 1, and 2. These values of L tells us the shape of the orbitals as follows. The value L equals 0 corresponds to an S subshell. The value L equals 1 corresponds to a P subshell. The value L equals 2 corresponds to a D subshell. So at the n equals 1 level, we have an s orbital or an s subshell. At the n equal 2 level, we have 2 subshells, that is, an s subshell and a p subshell. At the n equals 3 level, we have 3 subshells, an S, a P, and a D subshell. Now each subshell may be divided into individual orbitals. Each individual orbital is characterized by a magnetic quantum number m. M describes the magnetic moment of an electron in an arbitrary direction. m is always an integer and is dependent on L such that m can range from negative L to positive L. So let us take a look at a P subshell where L equals 1. In this case, m can take 3 different values. Negative 1, 0, and positive 1. These 3 values for m means that we have 3 individual p orbitals. For the d subshell where L equals 2, m can take the values negative 2, negative 1, 0, 1, and 2. So here we have 5 individual d orbitals. Let us now look at the s subshell where L equals 0. It follows that m equals 0 as well. So the s subshell only consists of 1 orbital. So in summary, we have broken down the shells into subshells, which are further broken down into individual orbitals. Each of them has their own distinct quantum number. The individual orbitals are regions around the nucleus where the electrons would be found. Each electron has a spin quantum number denoted by S. This spin quantum number describes the spin of each electron. The spin quantum number S can either be plus a half or negative a half, otherwise called spin up or spin down. So here we have 4 different quantum numbers. We saw how L is dependent on N. And we also saw how M is dependent on L. So it follows that an electron with spin S can be described by these 4 quantum numbers.